Good evening. This is Kawagesa Adim, and I'll be taking you through large acoustic models for visual narration with large visual embeddings. Beginning with the definitions of the keywords, large acoustic models, these are deep learning models that are trained on vast sound datasets to make an understanding of the audio context. And then another key term is large vision models. These are also advanced AI models that are trained on vast image datasets to make understanding out of the images or videos. Then you have large visual embeddings. These mean embeddings just mean numerical representations of different images in a way that a computer can easily understand, because you know images they shouldn't be taken as just pixels, but in a numerical perspective that a computer can easily understand. Then another thing is visual narration. We have to make sure that the scene can easily be narrated to someone who can't easily see, or someone who's visually impaired, if I'm going to relate it to the perspective that I'm talking about, a project that I'm talking about. Then another key term is scene understanding. Scene understanding, this one means like how it sounds. It's deriving semantic meaning out of the scene in a way that you can easily narrate it to someone who is unable for that. And the next slide shows a table of contents. And I'll be talking about in this presentation. And then beginning with the introduction, we know that for million visually impaired people or the blind, uh, images and video is a close word to them. Even when some other systems or other systems have been improved, have been developed. For example, let's say for the audio descriptions in videos, let's say the outtakes to explain the images. These ones are literal and shallow in that they don't bring out the details of what is taking place generally in a scene. So we have to ask ourselves a question: what do these blind people or the visually impaired, what do they miss? Of course, when someone loses sight, or when someone is born without that thing of seeing, they miss a whole layer of human experience that vision comes with. It's not about okay, it's all about the emotions. Of course, they miss the emotions, they miss the social cues. For example, when someone waves at them, they can't easily know who has waved at me. When someone okay, yes, they can hear, but of course they can't see what's taking place in the environment. So they miss a lot. They miss the emotions that comes with that. They miss the social cues. They miss the spatial awareness. So it's a lot that they miss. And in a nutshell, what they miss is they miss the chance to explore and experience the semantic understanding of the whole environment that is surrounding them. So how is that a problem, and how is our project solving that problem? We are going to see that um, in a way that a vision helps humans capture context and meaning their surroundings. That's what I've been explaining in a few minutes. And these blended visuals miss the ability to explore and experience the semantic meaning of the visual scenes. And the current assistive tools, they mainly focus on, let's say, object detection. For example, uh, let's say these guide sticks, these the guide dogs, most of them are just there to don't hit this obstacle, but they don't give out that semantic understanding that someone who is not into seeing can understand what's taking place in the closed world that they can't reach. So our system, our project integrates the large visual embeddings and the large acoustic models, translate visions into expressive narration, like how we're going to be seeing in the methodology. And the computation problem, I'll be explaining further how this is a problem that people who don't see, because we realize these people who don't see, they don't get the semantic understanding of the environment. And these existing systems, for example, let's say Siri, let's say ChatGPT audio, these ones they just give you an audio which is not descriptive, which is not context aware. For example, to say a dog, this is a dog, but it won't bring it out in a way that it sounds like human interaction, like human narration. For example, it has to say there is a dog uh, in a park playing in a park with kids playing. That's something that is more of human narration and can easily bring out a semantic understanding. Someone who can see, and that person can easily know, you know what, this is happening, in even when they don't see. So that's literally what our project is mainly focusing on, in that it can bring out that context of helping the blind people or the visually impaired being able to explore and experience the semantic understanding behind the visual aspects. All right. Going further, the works that we came up with, um, we are having the audio side. We cited a few papers, and more are there, but then these are just the samples of the papers that we reviewed. One is the audio side, which is the author is Ainari. It was raised in 2025. Its methodology lies between the multimodal large language models, the MLMs, that are integrated in real time for the visual analysis for context-aware interaction. But then this one has a problem, has a like it focuses more on dialogue-based interaction rather than continuous narration. Like I've been saying, for that, it's more like ChatGPT. It gives like a dialogue. Like, let's say you're having a conversation with someone. How are you? I'm good. Like, in that perspective of a dialogue, it doesn't bring out a semantic understanding of what's taking place. So it's a limitation to this audio side. Then another one is an all my eye. This one, it's more of a it's a wearable device translating printed text, faces, and objects into speech using computer vision. It mainly focuses on computer vision. It can even detect the barcodes. For example, people who want to do, let's say, they're at the till, they're shopping. So this system also helps them to make sure they can easily carry out the activities in a way that it can help them. But it mainly uses computer vision. But it has a challenge. It's dependent on good lighting, in that in times of darkness it doesn't perform very well, or dim light doesn't perform very well. Then another one, we're having synth audio, whereby this methodology lies in converting distant scenes into nonverbal audio using psychoacoustics, audio scene analysis, and Foley synthesis, combined with speech used for object localization. Object localization just means detecting where objects are, which place they're in, and their positions. But it has its limitations. Like, it's limited to distant scene representation. Like, it focuses more on things that are very far. It doesn't focus mostly on things that are in a stone's throw, that are very near to the person. So this is also a very big challenge. And then another paper is an investigation into using acoustic touch to assist people who are blind. Its author is Jane and others. It was released in 2023. It's developed its methodology. It's developed uh, a formatted audio device, a FAD, using AR smart glasses. It has smart glasses, and it also uses computer vision, like the My Eye and auditory icon sonification to help blind users locate objects. It also has that element of localization, detecting where objects are, and it focuses mostly on localization, like I've been saying, but it lacks that understanding of giving out a semantic understanding of what's taking place in scenes. Doesn't give that human-like narration. All right. So uh, the problem, going on to the problem statement, we know we have the domain application problem. Of course, like I've been saying, these blind people, they lack the semantic understanding. They lack the chance to explore and experience what's taking place in their environment. Either they can derive the semantic understanding. But then the conventional problem we are facing is how to transform complex visual scenes into high-dimension embeddings that can capture semantic relationships and align them with textual embeddings to generate accurate descriptive narration. How are we solving this? Of course, we are developing a system that can capture rich semantic and spatial representation from visual scenes. How are we doing? How are we going to do that? We shall be focusing mostly on the large vision model, like I'm going to be showing you the methodology. And then another thing is, we are developing a system that can align the visual and textual embeddings. How are we going to do that? Of course, we shall have the large visual embeddings and the text and the visual aligner that can bring all these embeddings into one corpus. into one system. Then we also have how can we a system that can generate coherent and expressive narration. This would be through the language generation models, in that it can bring out that touch of something to feel like it's human-like interaction, right? And another thing, going to the research questions and objectives. Of course, one of the research questions is how can large vision models capture both semantic and spatial features from the complex visual scenes? And this will be done mostly through using the large vision model, like how you're seeing it in the objectives. And then what techniques can improve the generation of natural human-like and contextually coherent, narrations? This is through building and training a language generation component that produces coherent, context-aware captions and narratives based on aligned embeddings. This is more of we shall be using the large visual embeddings to do that. Then how can visual embeddings be aligned? Of course, like I had said in the previous slide, we shall be now using the visual and the text aligner to make sure that we bring the visual embeddings and the text embeddings into one system that a computer can easily understand that. All right. And then going through the research contributions and outputs, of course, we developed a large vision model capable of extracting high-dimensional visual embeddings from input images and video frames. We also developed a visual to text aligner, like I've been saying, that converts visual embeddings to text tokens to be fed into the large generation model. Then also developed a GP2, which is a language generation model function on a VIST This is a data set for the purpose of generating short descriptive stories for the blind basing on the scene captured. Then our methodology is, of course, we begin with we get the image or video, then we do extraction. We understand this image using the visual understanding. We can be a large vision model, for example, it can be a VIT date. Then from there, after understanding the image and extracting the features from the image, you have the project head, the projection head. The projection head, what it does is um, it of course, now it has to get the embeddings from these images, and we have the embedding from images and the text. Of course, we have the captions. So what it does, it brings these, it extracts, it has to bring these embeddings now into one system, in that they can be fed into the language, into the large visual embeddings space. Then these large visual embeddings, of course, like I said in the beginning, these are just numerical presentations of the images, and these ones are now fed into a visual text aligner. The visual text aligner, what it does, it makes sure that the visual embeddings and the text embeddings align, in that they can be fed into the large language generation model like the ChatGPT-2, to make sure that it can easily understand what's taking place in the scene. And then from there we do the scene narration. Of course, this language generation model, it generates the human-like interaction, descriptive captions, and then they're fed into the scene narration, and then from scene narration we have the TTS, text to speech, which now this is a large acoustic model for the sound. This sound is now translated into a visual scene narration through speakers, for example. And then we did the ED expert data analysis on a set. We are beginning with Coco 2017. Like we are saying, we are having the annotation. Annotation just means more information that is describing what's taking place. It's a large data set for object detection, segmentation, and captioning. Its size, it has a lot of images, training images, it has validation images, and it has testing images. It also has annotations, like I've been explaining. These are different things that are there. And then these are the graphs that are generated from that. And another data set is this data set. This is a data designed for visual storytelling. It's free narrative generation by pairing sequences for images with human written stories. Its size there and the annotations are also there. These are the different graphs that we managed to come up with, the EDA results, distribution of data splits, sentence count per story, sentence count per split, like that. And then we have the model selection of, so far we have three models. We have the long generation model, charge the GPT-2. We have the large acoustic models, the Kokai text to speech, and also the large vision model, the VIT-DAT. And from there, we have the results and experimentations. This is the VIT-DAT. You can see the predicted caption is generated, but the caption is not all that accurate because the model still wants more pre-training in that it can generate, exactly the exact captions. And then they also have the image embeddings, like here you see the numerical vectors. We also have the also have the GPT-2 model, how it the story generated a family picnic in the park with children playing. A lot has to be done in this. And then we have the anticipated limitations and the counteraction plan. What are challenges are we facing? We are facing a challenge of data imbalance and we shall mitigate that through data augmentation, real-time performance bottlenecks. Of course, we shall be having model quantization, pruning, and efficient inference. Then generation of unseen environments. We are going to have domain adaptation techniques and test out of distribution samples to improve robustness. All right, these are the references we used, and thank you. Be blessed.